So in this class we will discuss another problem on torsion of multicell section. Here this section consists of a rectangular portion and a triangular portion like this, isosceles triangle. Dimensions, center to center dimensions, median dimensions are given here. This is 200 mm, this is 150 mm, this is 125 mm and this is also 125 mm. So from this geometry we can find that this distance from here to here it will be 75 because this half of this if you take it will be 100 and this is given as 125 hypotenuse. So this will be according to Pythagoras theorem from here to here this becomes 75 mm. Now in this problem he has given that this section is subjected to a torque of 10 kilonewton meter. Total torque is 10 kilonewton meter, that is 10 into 10 power 6 newton millimeter. So the total torque consists of two torques, T1 and T2. So for the first cell, the torque is T1, for the second cell, torque is T2. The total torque is 10 kilonewton meter. And I will take this bounded area of this first cell as A1 and the bounded area of the second cell as A2. Now we can find out A1 and A2. So A1 is the area of this bounded area of the center line, which is 200 into 150, which becomes 30,000 millimeter square, and A2 is the area of this triangle. So half into base is 200 and height becomes 75. So half into 275, that is 7,500 millimeter square A2. And he has given the value of this shear modulus or the modulus of rigidity G as 80 GPa or 80 into 10 power 3 MPa Newton per mm square. In this question he has asked what are the shear stresses that are going to develop in the walls of the tube. So I will take the shear stresses as τ1, τ2 and τ3. So I will take this first cell subjected to T1 has got the shear stress τ1. And second cell, which is subjected to torsion T2, it has the shear stress τ2 and the middle web portion. So this is the web portion. In this web portion, let us take the torque the shear stress as τ3. Now if you take the point A here at the junction, so at the point A you can see that τ1 is acting like this. I have assumed like this. τ2 I have taken like this. τ3 like this. That means this τ1, which is the shear stress, and q1, which is the shear flow. So it is divergent, it is split into two parts, q2 and q3. That means the equation is q1 is equal to q2 plus q3. So it is like this. So this total part of q1 is split into two parts, shear flows in second and third one, that is q2 plus q3. So that is one equation. So first equation is T is equal to T1 plus T2. Second equation is Q1 is equal to Q2 plus Q3. So using those two equations, we can get the relationship between τ1, τ2 and τ3. Now we know that shear flow Q is given by the product of shear stress and the thickness. So here Q1 is the shear flow in the first cell. So first cell. So its value is τ1 into T1. So τ1 is not known here. T1 is 2 mm. So he has given this thickness as 2 mm. So therefore it is 2 into τ1. Next Q2 is τ2 into T2. So τ2 is not known. T2 is 5 mm. Thickness of this tube. So this portion is 5 mm. So τ2 into 5, that is 5 τ2. Then Q3 is τ3 into T3. That is thickness of this middle portion, that is web portion. That is 10 mm. So 10 into τ3. So these are the relationship between your shear flow and shear stress. Now by taking the equation T is equal to T1 plus T2, so T is given as total torque is given as 10 kilonewton meter, that is 10 into 10 power 6 newton mm. This should be equal to 2 into Q1 A1 plus 2 into Q2 A2. So we know this relation. So T is equal to 2QA. So this relation we know. That is applied for both the cells separately and we have to add. So that means here if you substitute that 2 into Q1 is 2 τ1 into A1 is 30,000 plus 2 into 5 τ2 that is Q2 into A2 is 7,500. So if you simplify this you will get the equation of this form 1.2 τ1 plus 0.75 τ2 is equal equal to 100. That is the simplified form of this equation. So I will take this as first equation. So from the torsion equation we got this equation. Now from the shear flow equation, which I have already told, Q1 is equal to Q2 plus Q3. So if you substitute for Q1 as tau 1 T1, so tau 1 T1 is equal to tau 2 T2 plus tau 3 T3. That means here once again tau 1 is not known, T1 is 2 mm, so 2 tau 1 is equal to tau 2 is not known, T2 is 5 tau 2 plus tau 3 is not known into T3 is 10 mm. So it becomes 2 tau 1 is equal to 5 tau 2 plus 10 tau 3. So this is the second equation in terms of tau 1, tau 2, tau 3 by taking the shear flow equation. Now the third, because there are three unknowns here, tau 1, tau 2, tau 3, we need one more equation, which is something called your compatibility equation. This I have explained in the last lecture also, the last problem. So the compatibility equation is this: the angle of this stress remains same throughout. So that is theta 1 is equal to theta 2, that is equal to theta. So here once again, if you use the compatibility condition in terms of shear stress, so it can be written like this. Here please note that, so first the 2 g theta is equal to tau 1 s1 plus tau 2 s2 divided by a1. So for the first cell, if you take for the first cell this one, so tau 1 is the shear stress here, multiplied by s1 is the distance. It is the distance over which that tau 1 flows. So that shear flow distance is your s1. In this case, s1 is tau 1 is acting here, here and here. So if you add these three from here to here, it is 150. Then this is 200. This is 150. So it is totally 500 mm. So 200 plus 150, 1 plus 150 is the value of shear flow in the first cell. Second cell, so it is shear. The length is the distance is s2. So this one you can see here, tau 2 is acting here and here. Only these two portions, which is 125 plus 125. So S2 is 250 mm, 125 plus 125. And S3 is the shear flow in the web portion. The distance is here, the distance is 200 mm. So S3 is 200 mm. So these are the values of S1, S2, S3 corresponding to tau 1, tau 2, tau 3. Now substituting these values in this equation, so you will get in this equation, these two. If you substitute, so tau 1 is not known, into S1 is 500 plus tau 2 into S2 is 250 divided by A1 is 30,000. See here. This should be equal to tau 2 into, now here you see this is you have to take negative because I have already told you that this tau 2 and tau 3 they are going now in different directions. Whereas in the first one, in whatever direction tau 1 is flowing, in the same direction tau 2 is also flowing. That is why we take plus sign here. So whereas in the second case, so in whatever direction tau 2 is flowing, tau 3 is not flowing in the same direction. Therefore, we have to take the difference here. That is very important. So substitute here, tau 2 into S2 is 250 minus tau 3 into S3 is 200 divided by A2 is 7,500. That is the area of the second cell. Now if you cross multiply and if you simplify and bring it to the simple form, this equation reduces to this form, tau 1 minus 2 tau 2 plus 2 tau 3 is equal to 0. Now you have three equations and three unknowns. First equation is this, second equation is this, third equation is this. So first equation we got from the torsion equation, second equation we got from the shear flow equation, third equation we got from the compatibility equation. Now by solving equations 1, 2, 3 for the three unknowns tau 1, tau 2, tau 3, we can find out them. That you can do with your calculator only. So these are the values you are going to get. Out of which this tau 1 is the highest value. So that itself is your maximum shear stress, tau maximum. Now after that, if you want to find the angle of twist, you can take any one of these, either this or this. If I take this one, theta is given by tau 1 s1 plus tau 2 s2 divided by a1 into this 2g will come to the denominator. You see here, this is how we can write. Now once again substitute all the values. Tau 1 is 60.6 into s1 is 500 plus tau 2 is 36.36 into s2 is 250 divided by a1 is 30,000 into 2 into g is 80 into 10 power 3. So that's what we have to substitute in terms of result per unit square AP. If you simplify this, you will get theta angle of twist per unit length as 8.10 to 10 power minus 6 radian per millimeter. So that angle of twist is represented as the radian per unit length or millimeter. If you want the total angle of twist, then if the length of this section is given in the third direction, so if the length is given, you have to multiply that length in millimeters to get by this value of theta to get the total angle of twist. So this is another example wherein given the torque and the rigidity modulus, how to calculate the maximum shear stress or the shear stress in all the different segments of the section, and what is the angle of twist for the entire section, because angle of twist remains same for both the whatever may be the number of cells by compatibility equation, angle of twist remains same for all the cells. Theta 1 is equal to theta 2. So always this can be expressed, 2g theta can be expressed in terms of the shear stress using this form in the form of a compatibility condition. So this is how we can analyze a torsion problem with multi-cell section. So multi-cell means more than one cell. So you can have irregular shape also. So these types of problems are important in torsion.